Hi, welcome to my channel. In this video, I am going to explain about the linear support vector mission classification. So, linear support vector mission classification, or it may be is one of the part of the support vector mission classification. It is a powerful, versatile machine learning model. It performs the linear or nonlinear classification and regression as well as outlier detection. So here we can see the what is meaning of a linear nonlinear classification. So here, for example, the support vector mission classification contains two types of things are there. One is a linear classification and a non-linear classification. Non-linear classification. Okay now. So here the data points are look like there are two types of points are there. Two class labels are there. Okay, these are the one data points and the data points like minus. Okay, these are the minus negative points and above are positive points. Our aim is we have to separate these 2 points linearly. So with the help of one line equation, okay, or any one line equation, we can separate the data points into 2 classes. This is one class label and this is another class label. Okay, with the help of linear classification, linear model. With the help of linear model, we can separate these 2 points into separately. So that's why this is called as a linear classification algorithm. Linear classification algorithm. And one more technique is called as a non-linear classification. For example, here the data points look like positive points, and these data points are non-linear fashion. The data points are in the form of a non-linear fashion. Okay. So at that time we are going to use the other data set. Here the data points are here in the form of a non-linear fashion. Okay. Now at this case we are going to use the data points in the form of a non-linear fashion. At that time we are going to use the technique called as a the model is called as a non-linear model. That model is exactly classify the data points of the positive class and negative points. Therefore, for non-linear fashion. So that's why the model, the SVM classification is both the linear classification as well as a non-linear classification. Okay, it is also applicable for the regression, or you can also apply for this one is for the identification of outliers. So SVMs are particularly well suited for the classification of complex data or small data set or medium sized data set. That's why the SVMs are one of the best algorithm to classify the linear separable data set or non-linear separable data set. And also it is applicable for the large data set or small data set or medium sized data sets. So that's why this is one of the best algorithm to among all the classification algorithms. Okay, now here we are going to see one data set. That data set is called as iris flower data set. It contains 4 features are there: sepal length, sepal width, petal length, and petal width. The corresponding class labels are species. Okay. Now it contains 150 rows are there. So if you draw these are the among the sepal length, sepal width, petal length, and petal width. The petal length and petal width are very important features to visualize our model, our data points. Okay. Now here in this in the linear SVM classification. So that means here where support vector mission classification contains 2 models are there. One is a linear SVM classification, linear separable classification, and non-linear classification, non-linear classification. Okay, here in this class we are going to discuss about the linear classification. So here, if you draw the graph between the petal length versus petal width, petal length on the x-axis and petal width on the y-axis. So the distribution of these points are setosa, and these are called versicolor. Now, so this is the distribution of the versicolor points, and these points are belonging to setosa classes. Our aim is we have to separate these 2 points separately. So for that purpose, we have to we are using the linear model. what is the linear model? That there we can draw the one line equation or linear, okay, linear model that exactly separate data point into two parts. Okay, so that is the important of the our linear SVM classification. There are different lines that classify the data into two parts, but we are going to see the which line is the best suited for the our data set. Okay, now here in this diagram, okay, the model whose decision bound is represented by the dashed line is so bad. Why? So here, for example, the green line is nothing but the dashed line. The dashed line is one type of bad decision boundary. Bad decision boundary. Okay, now this decision boundary does not separate the data points into two classes separately. Okay, so this is one. Why means here the blue colors are separated into two parts. But our aim, what is our aim? We have to classify the setosa and the vesicle separately. But this model, the thick and the dashed line is the wrong model. So there are other two models like here red line or purple line. Okay, that separate the data points separately. But what happened here? The decision boundaries comes to close to the instances. Instances. Okay, here this yellow, this thick red color very close to this data points here, and okay, this blue color, and here the purple color is very close to this yellow color points and blue color points. So this is one of the drawback of these two models. Now these models probably not perform well on the new instances. Whenever giving the new instance, it may not be classified perfectly. Suppose if the data set is blue color very close to this here, and the yellow color points very close to this line. Okay, but what happened here? The model is wrongly classified as this blue color point is become a citrus color, and this yellow color point is belonging to versicolor. Okay, and suppose for example here for example this is yellow color point and this is a blue color point. This case what happened? The thick red color line, the decision boundary, it is separate the yellow color as a blue versicolor, and this versicolor point belonging to citrus class. That's why these two models are very bad models. Okay, it's not classified the new instances. It's not classified the new instance. Whenever you give the new instance, it does not perform well on the new data. Okay, so that's why we are going to use the another technique that is called as a linear itself of support automation. We are going to separate data points into two parts. So here the decision boundary, the thick line, on the right side of the figure, here the thick line is there that represents the decision boundary of a support vector machine classified. The line not only separate the two classes. So here the two classes are there. This is a one versicolor and this is a setosa class. So this line not only separate the two classes but also stays as far away from the closest training instances. So these 2 points are this line is far away from these 2 instances. Okay, so SVM classified as a fitting the widest possible state between these 2 classes. Simply this is called as a large margin classification. Okay, here we are going to maximize the distance between these 2 parallel lines. Okay, so we are going to increase the margin between these 2 parallel lines. So simply this type of thing is called as a large margin classification. Adding more training instance, if you are adding any new instance to our model, suppose out of the state, if you are adding the blue color here and here we are having the yellow colors here, the model exactly classify these 2 things. Okay, now so here if you are adding any new instances of the state will not affect the decision boundary at all. Okay, if you are adding any new type of data set, it will not affect our decision boundary. Okay, it will not affect any effect. Okay, so it is fully determined by the instances located on the edge of the state. So simply these are called as a support vectors. So based on these 2 points very close to these points, okay, we are going to draw the parallel lines. Okay, this type of thing is called as a support vectors. Now SVMs are sensitive to the feature scales, and in the left side of the figure we are having the vertical scale is much larger than the horizontal scale. So here, for example, the horizontal scale is between the 0 to 6 value, but whereas here it comes the scales between the 0 to 100. Okay, 100. If the vertical in this example, what happened? The vertical scale is much larger than the horizontal scale. So the widest possible state is close to the horizontal. The widest possible state is very close to the horizontal. Okay. Now after the feature scaling, so with the help of standard scikit-learn standard scaler, if the decision bound is on the right plot is much better. Okay, that means here what happened now? Suppose here going to standard the feature with the help of feature scaling, like z equal to x minus mu by sigma. If you apply this formula for our data set, all the features are converted between the -2 to +2. Whatever data points here 1, 0 to 6 and 0 to 100, all are converted between the -2 to +2, and also here the x dash also converted into -2 to +2. So at this case, if the margin is going to be very high. But whereas here on the left hand side we are having if there is no feature scaling, then we are going to the margin is going to be very less. Okay, this is very close to the horizontal possible. Okay, horizontal. So like that we are going to apply the linear SVM classification on the given data set. Okay, thank you for watching our video. In the next video I'm going to explain about the soft margin classification. Okay, thank you for watching our video. If you like the video, please subscribe, and thank you.